Hello and welcome back. In this video, we're going to leverage our chain rules for functions of two or more variables to come up with a implicit differentiation formula that is, in some cases, a lot easier to use than traditional implicit differentiation. So remember back in Calc 1, using implicit differentiation, say we have a function or an equation like this, right? X equals sine of xy plus pi y squared. And we want to figure out what, how y changes with respect to x, right? So here, here y depends on x. And let's see. Right, so how would we do this using Calc 1 methods? Well, we differentiate, right? We would apply derivative with respect to x on both sides of this, and we would work it out. And we're actually going to do that here because I want something to compare our next result to. So I just want to remind you how this worked before. So derivative with respect to x of sine of xy. Remember, y is a function of x, so we're going to need product rule inside there, and it's also a chain rule, right? This thing gets a little bit difficult, right? I don't know who loved implicit differentiation, but it can get a little bit messy. So here, derivative of the inside would be derivative of x, that's 1 times the second, y, plus the derivative of y, that's dy dx, times the first x. So that's the derivative of the inside times the derivative of the outside evaluated at the inside. So there's the derivative of this first term with respect to x, and derivative of pi y squared with respect to x. Remember, y is a function of x, so this is going to be a chain rule. So this will be plus 2 pi y times the derivative of the inside, which is dy dx. And then on the other side here, derivative with respect to x of x is just 1. And now we have to solve for dy dx. So let's expand this out, collect all our dy dx's, and solve for dy dx. So I'll have y cosine xy plus dy dx x cosine xy plus 2 pi y dy dx equal to 1. I'm going to take it up here. Again, I want to isolate all my terms with dy dx's in and bring everything else to the other side. So I'm going to have dy dx here times x cosine xy plus 2 pi y. And then over here, 1 minus y cosine xy. So that means, finally, dy dx is 1 minus y cosine xy over x cosine xy plus 2 pi y. Wow, what a problem. Lots of room for error in it, and yeah, it takes a little bit of time. So what we're going to use here, now that we have chain rules for functions of several variables, I'll show you how we can leverage that to solve this problem maybe a little bit easier. So the idea is, first what I'm going to do is I'm going to bring everything over to one side so that I can sort of define a new function here. So I'm going to bring that x, I'll have sine of xy, sorry, short-term memory is bad, plus pi y squared minus x. Pi y squared minus x equal to 0. So this is the same equation from before, I just have it set equal to 0. So what I'm going to do here is I'm going to define a new function of two variables. I'm going to call it big F of xy. And I'm going to define that to be sine of xy plus pi y squared minus x. And the interesting thing about this function is that it's always 0. Right? This function is always 0, so its derivative with partial with respect to x, partial with respect to y, it will be 0 as well because it's everywhere 0. So now let's investigate the relationships here. I have f, which depends on x and y. But remember, y is a function of x. So my sort of lowest variable here is x, the one that everything else depends on. And I know this is a funky looking tree diagram. Just remember that y depends on x, and we need to show that relationship here, right? All the relationships should be shown in this tree diagram. So now what we can do, if I want what I'm after is dy dx, but if I do this right, if I look at the partial of f with respect to x, so partial f with respect to x, let's write down the chain rule for that. So this is one way to get to x. So that'll be actually what I should say instead of partial f partial x, what we're after actually is just the single derivative df dx, and that'll be partial f partial x. I know this looks a little bit funny. Trust me, it's going to come together in a really nice formula. Plus, and then how else can I get to x? Well, that's through y. So that'd be partial f partial y times dy dx. And I'm going to write these in terms of, I'm just going to write fx for partial f with respect to x, and fy for partial f with respect to y, times dy dx. Now remember, big F of xy was just 0. It's identically 0 everywhere. And so this partial f with respect to x is 0. So this is all equal to 0. And I can solve now for dy dx. So dy dx is minus fx over fy. So isn't that cool? Here's a formula now for the derivative with respect to y, derivative of y with respect to x in terms of the partials x, partial derivatives of f with respect to x and y. So let's see if we can recover this then. Let's see if we can recover that formula. So there's my f. Remember, you got to bring everything over to one side to define your f, and then this formula will work out, right? You need it all to be equal to 0. That's how this works. So I can find, let's find fx, so derivative with respect to x. Well, that'll be what, y? Derivative of the inside would just be y cosine xy. That'll go to 0 minus 1. And then fy will be x cosine xy plus 2 pi y. And then the x is constant, so that goes to 0. So minus fx, that's going to be 1 minus y cosine xy. And finally, dy dx. So now we have all of our bits and pieces. Let's combine them according to this formula. So we'll have 1 minus y cosine xy over fy x cosine xy plus 2 pi y. Well, let's see. Did that work out? Compare the two. Yep. That works out. So that's pretty cool. In general, I think it's a lot easier of a formula for dy dx for implicit differentiation. It's a pretty cool little trick now that we have partial derivatives. All right, that's it for this one. I'll see you next time.